Okay. Um, so I wanted to start with a little bit of a review of what we covered on Wednesday since we had the bad weather and a lot of people were not able to attend. Um, Looking at, oops, get my stuff uncovered here. There we go. So we were talking about ratios and proportions. And we talked about a bunch of different ratios and actually rates, and then use them in proportions. So things like if we have 4,000 milligrams of medication to administer, remember we're just going to use the generic term serum for medication or any other active ingredient. And we're going to do it at a rate of 50 milligrams. Let's just do 500 milligrams per hour. First, remember we said when we saw a rate like that, 500 milligrams per hour, we need to think full scale. That is an abbreviation for this unit rate, 500 milligrams over 1 hour. Remember, it's called a unit rate because that second number has a unit, but its value, the numerical value, the count is 1. And so then we can put that in a proportion. And when we put a rate within a proportion, we also said that the units over here had to match up. This is milligrams, so this has to be milligrams. This is hours, this is going to have to be hours. Well, looking at the numbers we're given here, the 4,000 milligrams, that would have to go in the milligrams on top. And we want to figure out how long this would take to administer. So we're going to find the hours. And so we cross multiply 1 hour times 4,000 milligrams. That's 4,000 milligram hours if we're using the units. Remember we said normally we'd leave the units out just so it didn't get terribly confusing. Then we divide by the other number, the 500 milligrams. 4,000 divided by 500 is 8. Milligrams divided by milligrams divides out, so we're left with hours, which is the units we wanted there. So it would take 8 hours to administer that 4,000 milligrams of serum of medication at that rate of 500 milligrams per hour. And we looked at ratios within our within our proportions as well. If we have a medication that we have to mix 5 milligrams in 2 milliliters of liquid, and we want to know how much liquid for 200 milligrams of serum, of medication. And actually I ended up with a rate again, but we'll go ahead and work with it. This is 5 milligrams in 2 milliliters. So that is our rate. Remember, it's a rate because they're different units. And over here we have 200 milligrams. That has to go on top. We want to know how much liquid. We'll cross multiply and divide. 2 times 200 is 400. That would be milliliters, milligrams. This is milligrams times milliliters. Divided by the 5 milligrams. So that would give us milliliters here. 400 divided by 5 is going to be 80 milliliters. So that would be mixed into 80 milliliters. So more of a true ratio would be, we're going to mix 5 milliliters of a concentrate into 40 milliliters of total solution. So we want to know how much would be in 200 milliliters of solution. So this is a ratio. We have 5 milliliters in 40 milliliters. Now the 40 milliliters is total solution. So on the other side, whatever goes on bottom has to represent the amount of solution. How much would be used if we had 200 milliliters of solution? That is the solution, so it goes on bottom, 200 milliliters. Now again, because this is a ratio, the units are the same, so we can actually cancel out the units on the left side. We don't need those because they're the same. But we are going to keep the units on the right side because we know that milliliters then has to be the unit up here. Those two units do have to match up when these are ratios. And then we'll cross multiply and divide. 5 times 200 milliliters is 1,000 milliliters. Divided by 40 is 25 milliliters. So it would take 25 milliliters of that serum or medication in a 200 milliliter solution at that ratio. So this cross multiply and divide is the shortcut that we've learned. We also saw that there was a longer process behind that. It might have looked like this. Let's do 5 over x equals 20 over 32. And here we could cross multiply and divide, but let's go ahead and do the longer process. The longer process is to cross multiply and set the cross products equal to each other. So in this direction, we have x times 20 or 20x. That has to equal the other cross product. In this direction, 5 times 32, which is 160. Then we solve for x by dividing by 20. And that's actually where the divide came from in the cross multiply and divide. We know that to solve the equation in a simple proportion like this, we're going to end up dividing. So we just did it rather than writing out the equation. So dividing by 20 gives us x. 160 divided by 20 gives us 8. But we can have more complex proportions than that. We might have 6 over 15 equals 5x over 25. So here, cross multiplying and dividing would not work because the variable or the missing piece is not by itself. It's not taking up a whole quadrant of our proportion. So here we would want to do that full cross multiplying. Going this way, we have 5x times 15, or 15 times 5x, either way. That has to equal, going this way, 6 times 25 is 150. And then we have a little work to do. We got the 5x times 15 is 75x equals 150. Now we can solve. Dividing by 75. X equals 2. So now depending on what we're trying to find, if we wanted to find the value of x, x is 2. If we were trying to find the value for that portion there, then of course it would be 5 times x, or 5 times 2. Well, it can get even more complex than that. We can run into, let's do 3x minus 5 over 25 equals 5x plus 5 over 75. So here, cross multiply and divide would do absolutely no good because not only is the variable not taking up, the missing part not taking up a whole quadrant or whole section here, but it appears in multiple quadrants. It appears both here and here in this proportion. So to solve, we have to do the full cross multiplying. So going in this direction, we have 5x plus 5 times 25, or I'm going to write as 25 times with the 5x plus 5 in parentheses. And that has to equal the other cross product. So going this way, we have the 3x minus 5 times 75. So again, I'll write the 75 first. Then in parentheses, the 3x minus 5. And now it's just solving the equation to find the value of x. We have to combine on each side. So over here, we're going to distribute the 25. 25 times 5x is 125x. And 25 times positive 5 is plus 125. That's all we can combine on the left side. Let's go to the right side. Here we have 75 times 3x. 75 times 3 is 225, so it's 225x. 75 times negative 5 is a negative 375. So we have combined everything we can combine on the right side. Now, we have to go to step 2 of solving an equation, which is to make sure the variable is on just one side. It's on both sides right now. The smaller one is the 125x. So we'll subtract 125x from each side. So on the left side, that's gone, giving us just 125 here. On the right side, 225x minus 125 is 100x. Then we have the negative 375. Now we have to solve for x. We're ready to solve. We're going to add the 375. Well, 125 plus 375 is 500 equals, all that's left on the right side is the 100x. And then we'll divide by the 100 to get x by itself. 500 divided by 100 is 5 equals x. So that's the value of our variable. So, like I said, these proportions can get as complicated as we need them to. Most of what we're doing here is just an exercise in simplifying the proportions. We are going to use the proportions quite a bit in our dosage calculation. Similar to these examples we saw up here, where if we know a certain dilution and we want to expand it to a greater amount of solution, or if we have a medication concentration and we need to know how much to have to get a full amount of medication, those proportions are going to occur a lot in our medical dosage calculations. So I promised in Unit 1 that we would come back to this in Unit 2. We want to talk a little bit more about percents. So we did a lot of calculations with percents. We used that proportion method for a lot of it. Things like blank is 40% of 30. We started with the percent. 40% was 40 out of 100. Equals, on the other side, we have to match things up. Blank is 40%, implies that blank matches up with the 40. Of 30, if you read that as out of 30, implies the 30 has to go on bottom. And then we solve this, since the missing piece does take up one full quadrant of our proportion, we can just cross multiply and divide. 40 times 30 is 1,200, divided by 100 gives us 12. This took on many forms. We might have 36 is 90% of blank. So again, 90% is 90 out of 100. Here, 36 is 90%. That implies the 36 goes with the 90. Of blank, again, if we read that as out of blank, that implies the missing number goes on bottom. And again, we cross multiply and divide. Now here, the two numbers that are diagonal are in this direction. 100 times 36 is 3,600. Then we divide by 90 to get 40. Oops. 40, there we go. So 36 is 90% of 40. And even if we were missing the percent, we had 42 is blank percent of 60. We still started with the percent, it was just blank out of 100. And now the piece we're going to be looking for is that missing percent, the top part of the 100 proportion. 42 is blank percent, implies 42 goes with the missing percent. Of 60, again, read that out of 60, implies the 60 goes on bottom. And we can cross multiply and divide again. 100 times 42 is 4,200. Divided by the 60 gives us 70. So 70 out of 100 or 70%. We have to be a little bit careful how we state that one because it's not 70 is not our answer. It's actually the full 70 out of 100 or 70% there. Well, we also explored the rate method, and we've actually used that when we did our solution concentrations. Where we saw that the amount of serum, that's that active ingredient in a solution, was found. Let's say we have 400 milliliters of a 12% solution. We found the amount of serum by taking the rate of 12% becomes 0.12 times the amount of solution, 400 milliliters. That gave us that we had 48 milliliters of serum, of active ingredient in that solution. The application that gave us trouble on the first exam, and always does, so that's why there's only one problem like it on there, and we come back and do more of it here in the second unit, is markups and marks downs, and dealing with the word problems with them. So for example, let's say that Sam receives a raise from $16 per hour to $17.50 per hour. Find the percent raise. So this is a percent increase. And so when we deal with a percent increase, the percent over 100 is equal to the amount of the increase over the base amount. Now, we've used that term base amount before, talking about percents. In a percent increase problem like this, it can be somewhat unclear what the base amount is. The base amount in an increase problem is always the starting amount. So here the starting amount is the $16 per hour. So if we set this up, it is percent over 100. We find the amount of increase. Well, the amount of increase is we're at $17.50 now, and we were at $16 an hour. We subtract that, that's a $1.50 increase. Over the $16 per hour was the original amount. So that's the base amount. So then to find our percent increase here, we cross multiply. That's going to be the 100 times the $1.50. That's 150 divided by the 16. This won't divide out nice and neatly for us, but we'll get a percent. 150 divided by 16 gives us 9.375. So that is a 9.375% raise. So that ends up being. But on the other side of that, let's say that we have already had an increase. Let's say after increasing the dosage by 20%, patient is receiving 540 milliliters of fluid per hour. Find the original dosage. In other words, the dosage before the increase. And this is the type of problem that gave us a lot of trouble on the first unit test. So finding that original dosage, what we need to do is we need to look at what the percent is after the increase. So I'm going to do a little table here where we have an original dosage. And to that, we add an increase, and we get a new dosage. Now, each of these numbers in a percent situation, each of these items is actually described by two numbers. One of them is a percent, and the other in this case is milliliters. So for percents, we have the 20%, which is the percent of our increase. The 540 milliliters, that is the milliliters of the new dosage. That's after the increase. Now, it looks like that's all the information we have. But remember, in a percent problem, we always have the base amount. Remember, the base amount is 100, represents 100%. That's always the starting amount, or in this case, the original dosage. So that is 100%. And once we have filled in that, well, then we can do a little basic math. 100% plus 20% means the new dosage was 120%. Then we have to look for what are we trying to find here. We want to know what the original dosage was. That's this amount right here. Now, as I look at this table, there are two lines that I need out of this table. One line is the line that has what I'm looking for. Well, that's this one here. That only works if I have the other number, and I do. I have the 100% on the left side. The other line that I want to use is the line that has both numbers, both the percent and the milliliters in this case. That's the new dosage here. So if I just pull them out of the table, I got the 100 and the blank, and I've got the 120 and the 540. Now, this proportion is kind of upside down. If you wanted to, you could flip both of them over, have 120 over 100 and 540 over blank. That would be fine as long as the 120 and the 540 stay together and the 100 and the blank stay together. Doesn't matter which one really goes on top or bottom. And then we can cross multiply. 100 times 540 divided by 120. So we would do 100 times 540 divided by 120. Should give us 450, and there it is. 450 milliliters was the original amount before the increase. On the first test, so many of you tried to find the 20% and then subtract it. That doesn't work because the 20% does not come from the 540 milliliters. If you tried to do that, you'd get something like 436 milliliters. That is not, or 432 actually milliliters. Because the 20% comes from the 450, not the 540. You can only calculate percents if you know the base amount. And here we had to find the base amount. So we had to come up with some way to relate it. Being a percent increase, we had to add the percent increase to 100 to find what percent represented that amount. Or the other side, after a 15% drop in heart rate, the patient's pulse is 68 beats per minute. Find how much did the pulse rate drop. So, again, the 68 beats per minute is after the drop. That is not the base amount. We need to know that base amount. The base amount would represent the old rate, or the rate before the drop. I'm just going to say rate before. We're going to subtract from that a drop or a decrease, whatever word you want to use. The words aren't important. It's knowing what they represent that's important. And then we have the new heart rate, or the new rate, down here, after the drop. I could have also said after if I wanted to there. And again, here, each of these amounts is represented by two numbers. One is the percent, and the other one in this case is the beats per minute. So for the percents, we got the 15% drop, so 15% represents the drop. 68 beats per minute is the rate, the pulse rate after the drop. That goes there. Once again, the starting amount is our base amount. So I can put 100% up here for the rate before the drop. And now this is a decrease, so I'm subtracting the 15%. 100% minus 15% makes this 85%. Is the rate after the drop. So I have this link here. I have both the numbers for the new rate. What am I looking for? Well, in this case, I'm not looking for the original amount. I'm looking for how much the rate drops. I'm looking for this amount here. So the line I don't want is this top one up here. The middle row is the one that has what I'm looking for, and the bottom row is the one that has both numbers. I can just pull those out here. I have 15 over 85 there. That equals, on this side, it's blank over 68. And I can cross multiply and divide. 15 times 68 divided by 85. Which gives us 12. Which means the amount of drop, the decrease in heart rate was 12 beats per minute. And of course, we could use that if we wanted to find what the old heart rate or the original heart rate was. We could add it to the 68 to get 80 beats per minute. Or we could go back through and do 100% over 85 and do that calculation. So let's, another application of percents that come to us in medical situations is a tolerance. The doctor orders that a patient be administered 450 milliliters per hour of a solution, of an intravenous solution. But there's a tolerance of plus or minus 5%. So what does that tolerance mean? Well, tolerance, technically in manufacturing, the word is allowance, but our textbook tends to use the term tolerance, or you're allowed to be off by plus or minus 5%. What that means is we can be 5% away from that. So to find that, we start with the 5%. That's 5 over 100. The 450 is the base amount. And we cross multiply and divide. 5 times 450 divided by 100. Giving us 22.5. What that's saying is we are allowed to be off by 22.5 milliliters per hour. So that means is a range, acceptable range, for that flow rate to be flowing at is from 450 milliliters per hour minus the 22.5 milliliters per hour to that order of 450 milliliters per hour plus that allowance of 22.5 milliliters per hour. So if I subtract here 450 minus 22.5, that's 427.5 milliliters per hour. That's the minimum flow rate that would be allowable. Up to, we could add here, 450 plus 22.5 is 472.5 milliliters per hour. So there is our acceptable range of that flow rate. This can also come into play when we deal with equipment. So let's say we have an IV infuser that is only capable to the nearest drop. So usually we set an infuser drops per minute. This infuser can only be set to single drops. It can't be a 1/10 of a drop or 100th. Some infusers do go up to 1/100th of a drop per minute for their settings. But this one is only capable of going to the nearest drop. We're allowed plus or minus 5% error in our dosage, just like in the last one, 5%. But we calculate the necessary flow rate at 7.44 drops per minute. Well, if we can only set this to the nearest drop, that means we would have to set at 7 drops per minute. 8 drops per minute would be even further away from our calculated amount, so 7 drops per minute would be as close as we could get. But is that within the 5% error? Well, let's take a look. So 5% is 5 out of 100. And now again, we have to make sure we find the base amount. The base amount is the calculated amount of the dosage. That's the 7.44 drops per minute. And now we cross, multiply, and divide. So 5 times 7.44 divided by 100 gives us 0.372. Drops per minute. That is our allowable error here. We can be off by that much, which means the range would be allowed would start at our calculated amount of 7.44. And we would, I'm going to replace that. The abbreviation for drops is GTT. I don't want to get used to putting DR in there because DR is dram. So anyway, 7.44 drops per minute minus the allowance of 0.372 drops per minute to 7.44 plus the 0.372 drops per minute. So if we subtract here, we get 7.068 drops per minute is the minimum, and a maximum of 7.812 drops per minute. So we can see our infuser setting of 7 drops per minute is below the minimum for our range. So that infuser is not going to be capable of handling what we need. 7 drops per minute is not in the acceptable range. So we would have to go find an infuser that is capable of going to at least 1/10 of a drop per minute. Now, the other way we could have handled this one here, we could have calculated by finding the percent. We're finding the actual percent rather than just comparing it to the acceptable amount of 5%. And to do that, we would have done blank over 100 would be our percent. Our base amount is the 7.44 drops per minute yet. The amount that we've rounded, we've gone from 7.44 to 7. So we subtract that as 0.44 drops per minute. So man, this is 7.44 minus 7 to get that. And now we can cross multiply and divide. 100 times 0.44 divided by 7.44. Gives us 5.91%. 5.91 out of 100, or 5.91%. Which again is larger than our 5% of allowable error. So we know that is not an acceptable setting for us. So this is another important calculation. If any of you do decide to go into a medical field, whether it's nursing, CNA CNAs probably wouldn't deal with a lot of medication, but medical assistant, PA, or any of those fields, knowing whether the equipment is capable of meeting your needs is an important calculation and an important assessment. So in this case, 5% error, this infuser would not be capable. So then the question is, how big does the dosage have to be before we're guaranteed that this infuser will work? So in other words, at some point, the round off in the infuser is going to be less than 5% if we have a big enough dosage. So the maximum round off would be if we had like exactly 3.5 drops per minute or 6.5 drops per minute. The maximum round off would be 0.5 drops per minute, or half a drop per minute. If we want to stick to that 5% standard, 5 out of 100 equals 0.5 is the error, so that the 5 up here represents the error. So the 0.5 goes with that. And we cross multiply and divide. 100 times 0.5 divided by 5 gives us 10 drops per minute. So if our dosage is at least 10 drops per minute, then this infuser is guaranteed to be okay. If our dosage is less than 10 drops, our calculated dosage is less than 10 drops per minute, then we have to be careful about this infuser. If the calculated amount is getting really close to being right between drops, the round off error might be too much to be acceptable. Okay, so a couple of things here. We're a little early, but we'll get you going here. Homework. For those of you that weren't here on Wednesday, let me pull that one up for you. So from Wednesday, we had page 73, 1 through 39, the odd. So again, working with the proportion, the ratios, the rates, and then calculating in proportions. Then for today, the further applications of percents is page 78, 1 through 35, the odd. And I've only had a few students who have turned in test corrections. So if you have not done that yet, make sure you're working on those. If you have any questions, let me know. I'd be happy to help you through them. I did get Mauston, so you guys, if you look in the grade book, you'll know that your test corrections have been recorded. If you look in Blackboard, like let's say your grade is 98.51. Having that hundredths digit of 1 indicates that you have corrections are recorded and in the grade book. For the rest of you, if you have not done those yet, please work on those and get them to your contact person at your school to send to me. It does make a big difference in your grades. The last thing I wanted to address is it looks like we might have some potential weather issues coming up again Sunday evening. If that does affect us for Monday, what I've been told by the counselors at each location is they're encouraging you to log in from home on Monday. So regardless of weather, we will have class on Monday either way. If you can't log in from home, I will post the recording for you in Blackboard as always. So with that, we'll let you guys go. Have a great weekend, and hopefully we'll see you all on Monday.